Our last talk of the day is 5 years of hacking ICS and IoT in Pwn2Own. And it's my pleasure to introduce our next speaker, Sharon Brizinov, a leading expert in IoT and OT vulnerability research, and the head of Team 82 at Clarity. Sharon has over 200 CVEs to his name, and has shared at top conferences like DEF CON, Black Hat, and SANS. He's also a 5-time Pwn2Own competitor, a Master of Pwn, and recipient of SANS Researcher of the Year Award. Please put your hands together for Sharon Brizinov.
Cool. Hi, everyone. Nice to meet you. Thank you. So my name is Sharon Brizinov. I work in the OT field for many years in a company called Clarity. So in Clarity, we're doing a lot of ICS research. ICS is industrial control systems. Usually these types of devices you can find in critical infrastructure, like electricity, like water utilities, etc. So I've been doing a lot of this research for a long time. Our research team is called Team 82, and we publish our blogs and research in Clarity/Team 82. So you're welcome to see there. Everything that I'm going to talk about is already there. This is my lab, as you can see. It's a nice lab. This is actually just 2 cabinets out of 6 that we have of OT-specific devices, including PLCs, HMIs, and other type of equipment. And today I'm going to talk to you about our experience in Pwn2Own. So my team is researching a lot of ICS devices, and like 5 years ago, we heard that Pwn2Own are conducting a competition in ICS hacking. So we love hacking. We try to break things as much as we can, and we decided to participate. So in this talk, I will try to explain our methodology, how we research ICS devices, what type of devices we researched, and how we competed in Pwn2Own. So let's start from what is Pwn2Own. Just raise your hands. How many of you know what is Pwn2Own? Not a lot. Okay. So Pwn2Own are kind of hacking competitions that you basically need to hack a device, to pwn it, in order to own it. So you need to go upstage, just like I'm here on this stage, and show your exploit on a specific device, for example, Windows, the latest version, and you need to pwn it and execute remote code execution in order to get the prize. Usually, prizes are from a couple of thousands to hundreds of thousands, depending the complexity of the target. So we participated in Pwn2Own for 5 times, and I would like to explain to you about our progress. In the latest one, we won first place, and we got the award. And along the process, we got prizes in the hundreds of thousands of dollars because of our exploits. So there are 4 types of Pwn2Own competitions: IT, IoT, ICS, and automotive. We focused on IoT and ICS because embedded research is our forte. This is our niche, so we decided to focus on it and research mostly devices around IoT and ICS. In this talk, I'll focus more about the ICS. So in ICS, we have, specifically in Pwn2Own, we have 4 different categories of devices. We have SCADA servers, we have ICS protocols that are specific protocols in the SCADA domains. We have HMIs, and we have engineering workstations that are kind of the IDEs where engineers are programming their programs to transfer to the PLCs. So these are the main 4 categories, and there are different vendors, like different products from, for example, Inductive Automotive, Rockwell, Process OPC, and other vendors that are very unique and specific to the ICS domain. So obviously, we focused on these 4 categories. Now, in Pwn2Own, you have usually, in Pwn2Own ICS, you have usually 2 types of exploits that you can demonstrate. The first one is kind of obvious, remote code execution. So if you are able to land remote code execution on the device or the product, you get usually 20K. And because we're talking about critical infrastructure, so think about an exploit that does not land with RCE, but does denial of service. For example, think of a substation in an electrical company. If you do denial of service, obviously this is very critical. So they also let you do denial of service attacks, and if you are able to shut down an equipment or do some kind of a denial of service attack on ICS equipment, you get 5K. So obviously we are always trying to do remote code executions, but sometimes it's very beneficial to do a lot of denial of services, and you get multiplies of 5Ks. So let me explain to you about our strategy, and then we'll move to specific exploits and vulnerabilities we found. Now, obviously, the first thing that you need to do if you're competing in ICS hacking competition is you need to understand what is ICS, what is OT, and what is SCADA. The brief, like the concise explanation is that basically you can think of SCADA and ICS as something compute that does something physical in our physical world. For example, if we're considering a factory, then a machine in a factory is part of ICS or SCADA. Why? Because the machine can be programmed and it does something physical in our domain, in our world. For example, moving a robotic arm or filling bottles or lifting things. So it does something physical in our world. Now, the physical things called the field devices, these are what you can see here as conveyor belts. This is an example. But what's controlling the field devices are PLCs, programmable logic controllers. So basically, these are ruggedized computers that can survive in very harsh environment, and you can program them to do some stuff. For example, to move a conveyor belt. Now, two other components that are very important are Engineering Workstation. This is the IDE, the Integrated Development Environment, where you write the programs and then you transfer them to the PLC to program the PLC. And then the PLC commands and does something with all the field devices, like conveyor belts, like lifts, like fans, like motors. And the last component that's important in this case is the HMI, Human Control Interface. This is where the operator can visualize all the data and all what's going on to control easily the process. For example, you can stop or start the operation there. You can see, for example, what's the temperature, etc. So obviously, we learned all about ICS. We installed a couple of different PLCs and HMIs. So we had a lot of knowledge on ICS equipment. The second thing we did is we bought 2 Intel NUCs. These are small computers, and we installed ESXi on them, and then we installed dozens of different machines with different software. So we wanted to do a quick research, and sometimes we would install some software and we wanted to roll back. So ESXi with a bunch of different VMs was the answer for that for us, and it worked pretty good. We specifically bought Intel NUCs because they're pretty powerful computers and they were very, very cheap. The last thing we did, and it was a decision we decided 5 years ago, was to focus on a very specific protocol called OPC-UA. So in ICS and SCADA generally, you have lots of different protocols because this is a very old kind of domain that many different vendors decided to focus on their own homegrown protocols. And there became kind of a gap between all these vendors that cannot work together, so they decided all of them to standardize a new protocol called OPC-UA, and we luckily decided to focus on heavy research on OPC-UA 5 years ago. And if you can see here the graph, you can see that with time, all the competition contained more and more OPC-UA capable targets, and it became a very good gamble. So having a very knowledge have deep knowledge into ICS protocol stacks is very important when you do ICS research and obviously when you compete in ICS competitions. Specifically, OPC-UA, DNP, 3 Modbus, and DNAP are key protocols, and obviously we decided to focus and research all of them. Now, so this is kind of the basic methodology of how we started the research around Pwn2Own, but let me give you some ideas around how and what we did specifically in OPC-UA and how we implemented this across different products that used and support OPC-UA in the competition. So first of all, what is OPC-UA? So OPC-UA is, just like I told you, is a protocol that kind of standardizes how you can communicate between different products and equipment in ICS. So for example, we have HMI and SCADA that wants to read the data from a PLC that controls a water tank, for example, to understand what's the current level of the water in the tank. Normally, you would need to, up until OPC-UA, for example, you would need it to understand the specific protocol that the vendor that manufactured the PLC implemented. So for example, if it was Rockwell Automation, you would need to communicate with the PLC using SIP. If it was Siemens, it was S7. So OPC-UA came into the picture and basically decided to standardize everything. So now we have a unified server, OPC-UA, that can digest and receive all the information from all the manufacturers. So every manufacturer provides a driver to communicate, a network driver or protocol driver to communicate with their equipment, and everything is found on the OPC-UA. And now if you want to understand what is the water level, you can just query one server using OPC-UA. So this is a very welcoming protocol that changed how we communicate and operate in ICS. Now, specifically, who pushed the protocol is OPC Foundation. They really standardized everything. They created a very detailed documentation that I specifically read a lot of it. And they focused on the important things. First of all, it's open protocol, so it's an open standard. Everybody can support it. Everybody can read it. It's interoperable, so it can communicate and interact with different equipment from different vendors, which is very important in SCADA. And it's also secure by nature. So if you read the documentation, it's very secure. It has a lot of security options, and it went through a lot of different reviewers, including our team. Finally, they decided, in order to accelerate the use of OPC, they decided to release different packages in different programming languages, so C, Java, etc. And so companies took these libraries and added more code on them. So what we have today is that we have multiple companies that are providing OPC capable software or product, that most of it is, as you can see here, most of it is laid upon or based on the OPC Foundation original libraries. And this is very important because when we started to research all the libraries and all the products, we came to the conclusion that essentially everybody are using the same base code. So obviously we decided to research the base code and find vulnerabilities that will be shared across many different products. And this is exactly what we did. So we researched the documentation. Again, it's online, it's open. So we researched heavily the documentation, and we started to ask ourselves questions. For example, if you can see here, the relevant part in OPC-UA that discuss the message header, you can see here that we have 3 different message headers. An intermediate chunk, so something that you transfer, but this is intermediate, the final chunk, and another variation of the final chunk. So when we looked at this, this type of documentation, and when we saw the flag is final, we asked ourselves, what happens if we're not providing the server the final flag? So what if we're continuously sending information to the server? I keep that in question open because I'm going to answer it in a bit, but after we heavily read the documentation, we decided to build our own OPC-UA protocol stack. So basically, we read all the documentation and we started to build our own Python-based client. And this was very beneficial because now we can control every aspect of the message, every bit, every flag, every byte. So we can really send customized messages to the server, and we can build very reliable exploits using our own infrastructure. So we built our own client. Another thing we did is we took a lot of libraries and we started to fuzz them, and we started to receive a lot of crashes. Because that was helpful, because now we started to understand where is the good code, where is the bad code, and this was very easy to do because these libraries, they were very easy to interact with because, again, OPC Foundation provided a lot of documentation how to use their libraries, and so all we needed to do is to write harnesses. We also used BooFuzz. This is a network fuzzer, so very easy to implement and set up. So think of, we have in our VMs different products running OPC-UA servers. So we just wrote a BooFuzz fuzzer to interact with them over the network and try to find bugs. And this was actually very beneficial again because it did find a vulnerability that I'm going to discuss in a bit, that resulted with a full RC, and we got 20K for that. This is how we found the bug. We actually created a video for that. So you can see we're running a lot of instances of BooFuzz, trying to fuzz network packets in OPC-UA, and actually found the crash. So I'm going to discuss it in a bit. Eventually, if we wrap up the 5 years that we've been researching OPC-UA, not only we were able to find vulnerabilities and exploit them, but we also developed like specific attacks for OPC-UA. I'm gonna discuss some of the attacks, but these are not just vulnerabilities in one protocol stack. It's actually a vulnerability or a common mistake that we found in many different products because they implemented a very similar code in each other. So let me give you an example. So this is OPC-UA denial of service, the chunk flooding attack, as we call it. And as I told you, in OPC-UA, we have 3 different header message. And we can see here in Wireshark that there is a byte that says what is the chunk type. For example, if it's F is final or anything else is intermediate, which means the server is waiting for the final chunk. So we looked at the code, for example, in one of the libraries, the .NET libraries in OPC-UA, and we saw there is a code that actually waits to the final chunk. And unless we're getting the final chunk, there is no return true for this case, which means the server keeps on waiting for more and more chunks. So obviously what we did is we sent a lot of chunks using the C type, and we just never sent the final chunk. So we kept bombarding the server with C chunks until it crashed. And as you can see here on the top right of the screen, this is not just one vulnerability, because this simple vulnerability, just by reading the documentation and asking questions, resulted with, I think, dozens of vulnerabilities in different products that implemented OPC-UA, and they implemented their own version of OPC-UA, but they had the same common vulnerability. No one of the developers asked themselves what happens if the client never sends the final chunk. So we just kept bombarding the servers. And we also presented this in Pwn2Own as an exploit, and we got a 5K for this. Another example, again, just by reading the documentation and asking questions, is method calling from a dead session. Again, this is another broad attack that we developed. And in this case, it's very interesting because OPC-UA servers can actually have consist functions, so user-controlled functions. So you can write your own function, and you can invoke this function remotely. So for example, you have a server, there is a specific function in the server that you can call from a client. Now, we asked ourselves what happens if we invoke the function and then terminate the session. what happens when the server wants to reach back to the client and send the result information back to the client. So what we did is we created an array of calling functions. So in OPC-UA, you can actually create an array of call method requests. So this array can be very large, and you can send basically a lot of calling method requests at once using this array. And then we terminated the session. So we're sending all of these call requests to the server starts digesting all the requests, then in the middle we're terminating the session, and then when the server finish to run all the methods and want to return the result back to the client, we're disconnected and it results with access violation because the object is dead. So this is again one of the attacks we presented in Pwn2Own, and it resulted us with 5K. Another example, which is a bit more interesting obviously, is remote code execution. So as I told you, one of the fuzzers we ran was a network fuzzer, and it actually found a nice vulnerability that resulted with remote code execution. So this vulnerability we found in PTC-Kepware. This is a very popular Windows-based OPC-UA server. And we, again, installed it in our ESXi as part of all the other products that we research. And we let our fuzzers just run on it while we're reading the documentation, while we're doing other stuff. And one night, we received a notification via Slack that our fuzzers found a crash, this exact crash, as you can see here. And we started to investigate what happens. So apparently, what happens is in the specific server in Kepware, they were having a proprietary code that tries to translate from UTF-8 to UTF-16. And this code tries to understand how much memory it should allocate for the new converted UTF string. So for example, if you're sending AAA, it knows that A is ASCII-based one, so if it needs to convert it to UTF-16, it needs to allocate 2 bytes for each character. So basically, it's a very complicated code that tries to understand how much new memory it needs to allocate. And the fuzzer, not us, to be honest, the fuzzer found a bug because it just fuzzed different strings, different information, different data, and just it found a bug and it crashed. So we looked at the crash and we saw something like this. So the client, the fuzzer sent AAA and then C3. And when we looked at the code, what happens, we saw that when the server tries to calculate how much new space it needs for the UTF-16 string, it will go, okay, this one is 1, 1, and then for C3, the server knows that it needs to allocate 2 bytes, so it jumped above the null terminator. And when it jumped above the null terminator, it basically reached other code because the null terminator should have, but did not finalize the string. And so we're able to use this primitive both for leaking and for writing on the heap. So basically, we used this out-of-bound read both for leaking pointers to defeat the ASLR, and also as out-of-bound write to construct a probe chain in the heap, and it lands us with remote code execution. By the way, we triggered this bug using the read and write tags. So in OPC-UA, you have this concept of tags that you can basically can read the current amount of water in the tank, or what is the temperature. Every aspect of something physical in our world can be constructed using what in OPC-UA we call tags. So we can read and write tags, and we use this primitive to both read and write, to leak and to jump into a rope chain in the heap. So we constructed our exploit, and then we run it in the Pwn2Own competition, and it landed us with a full remote code execution, and we got for this 20K. By the way, because there is a lot of content, obviously, I'm not getting into the details of exploit, but it's in our blog, so you're most welcome to read it. So if I'm doing kind of an intermediate summary for the OPC-UA research, we in Pwn2Own not only found a lot of different bugs and CVEs for both denial of service and remote code execution, but we also converted these bugs into attacks. So we created a framework for OPC-UA exploitation that you can use to execute attacks against a wide range of products that are using OPC-UA. And this resulted with around 50 different CVEs. Because again, you can think of an attack that worked across like 12 different products because they used the same shared code or for something very similar. So this was a very heavy research that we finalized, I think, a year ago, but it was a very long research, and we did a lot of disclosures with all the vendors in the ICS domain. Another cool exploit and vulnerability we found was not in the SCADA servers, but in the SCADA clients. So SCADA clients, as I told you, needs to read information about what is happening in the process. For example, it's asking what's the temperature, what's the current amount of water in the tank. So we decided to ask ourselves what happens if a benign client, like a normal client, is querying our server, and our server is malicious. Can we execute code on the client? And the answer, obviously, if I'm talking about here, is yes. And we were able to execute code on clients that queried our malicious server. So we focused on two servers, Ignition and Softing. These servers, SCADA servers, has OPC-UA functionality. So we created our own OPC-UA server, malicious server, and we used these clients to query our server, and we started to research what is the potential attack vector. I'm not sure if you can notice, but these these clients, sorry, are web-based, which means they run web functionality. So obviously we focused a lot of web research. Now, whenever you connect with a client, OPC-UA client, to a server, you can query all the different tags that you can read from the server. So you can see here, so we have different tags. For example, Clarity OPC-Pwn server, and we have aliases, and we have secret object, and we have secret variable. So all of these are tags that we can read. Now, we asked a simple question. In web, XSS is a very common attack. What happens if one of these tags is actually XSS-based object? So obviously, the attack here is that the client wants to read the water level tag. Our server says, OK, sure, here is your tag, basically hands over XSS injection, and then the XSS is interpreted in the DOM of the client, and we get XSS in the client, the OPC-UA client. So this is one example. This is another example. And surprisingly, there were no protections at all against XSS, because who would thought that in OPC-UA clients and SCADA servers there will be malicious OPC-UA servers. This is like not a common thing to think about. But we were able to exploit it in Pwn2Own. They offered these products as targets. So why not? But now we only have XSS. So how do we convert this XSS into RC? We continued to research the functionality of the clients. Now, obviously, we're in the context of the logged-in user, because a logged-in user is using the client to query our server. So what functionality can we use in the client to convert this XSS into RC? And it was quite easy, because it turns out that OPC-UA clients, specifically the two that we researched, had functionality to execute code very easily using a scripting language. So what we did is we created an XSS that runs in the context of the user, and it creates a new script in the client. The client, again, runs usually on Windows or Linux, but we can just create a script using Python, and we got RC on the client using this simple trick. So it's like a user would create a script inside their account, and now we have a full chain from client querying the server, receives XSS payload, the XSS will create and execute a script on the client, and we got RC for that. As I told you, whenever we encounter a vulnerability, we're trying to kind of try it on different products, and it actually worked on multiple products, and we were able to find more bugs and more vulnerabilities that we obviously disclosed to all the vendors. So, what is Pwn2Own impact on the ICS industry? To be honest, Pwn2Own really pushed us to find a lot of vulnerabilities that are deep inside ICS products, and we just uncovered a lot of critical ICS vulnerabilities that we would not research unless we had the incentive due to Pwn2Own. Not only the monetary beneficiary, but also the excitement of going on stage and a competition to participate in an ICS hacking event. So this really drives us as security researchers to try to find new things, but it also drives the entire ecosystem and entire community to a better and more secure world, because eventually these devices and products run in critical infrastructure, electrical companies, water utilities, factories, etc. So that's it. Thank you very much. And if you have questions, you're welcome to read everything in our blog or reach me out. Questions? Okay, if you're shy, you can reach out on private. Thank you.